Hi, I'm Mike Kultgen, Design Manager at Linear Technology. Today I want to show how the LTC6804 IC can improve the performance and reduce the cost of high-voltage lithium-ion battery packs. Here's the block diagram of a battery pack used in electric vehicles and power backup applications. Series-connected lithium-ion cells are monitored by ICs like the LTC6804. These ICs measure the voltage, current, and temperature of each cell and pass the data across an isolation barrier to a control circuit. The controller uses the data to compute the state of charge of the cells. For long life and safe operation, the state of charge is not allowed to fall below 20% nor exceed 80%. The first cost-saving feature of the LTC6804 IC is its 1 millivolt of measurement accuracy. Poor measurement accuracy can create uncertainty in the state of charge. 5% uncertainty means the battery pack must be oversized by 5% to guarantee some minimum capacity. Adding 5% more battery cells to a 16 kilowatt-hour battery pack costs about $450. With the 6804's 1 millivolt of measurement accuracy, the state of charge can be estimated within 1% and no extra cells are needed. Several IC suppliers claim to have 1 millivolt of measurement accuracy. Data shows that these ICs can lose their accuracy in the field. The second feature of the LTC6804 is measurement stability. The 6804 maintains its accuracy in harsh conditions, and here is why. A typical measurement IC has a multiplexer, an ADC, a voltage reference, and a serial interface. Measurement errors from the multiplexer can be eliminated by allowing enough settling time for the ADC to measure the cell. Component trimming eliminates the errors from the ADC. The fundamental limitation of the measurement accuracy comes from the voltage reference. If the voltage reference drops by 3 millivolts, the cell readings appear to increase by 3 millivolts. Measurement ICs are trimmed so that the initial value of the voltage reference is precise. Unfortunately, some voltage references will change dramatically with time, temperature, humidity, vibration, and circuit board assembly stress. The LTC6804 uses a new zener voltage reference to maintain accuracy under harsh conditions. The 6804 represents a significant improvement over the previous products which use a band gap voltage reference. For example, circuit board assembly can really affect voltage references. The ICs are subjected to 3 thermal shocks from the soldering process. The silicon experiences mechanical stress from the expansion and contraction of the plastic package and the copper lead frame. A band gap reference behaves like a strain gauge, converting the mechanical stress into voltage changes. A zener reference is almost immune to mechanical stress. This data compares 3 families of ICs. 3.3 volt cell measurements are taken before and after board assembly. The x-axis is the additional error caused by the board assembly stress. Our previous product, the 6802, and a competitor's product use a band gap reference. The additional error is almost 2 millivolts. The LTC6804 has less than 0.3 millivolts of error after board assembly. Humidity is another consideration. Moisture seeps into the plastic package and alters the mechanical stress. Here we compare the LTC6804 and a competitor's IC. The ICs are subjected to humidity at 30 degrees Celsius for 2 days. The band gap based product has almost 0.6 millivolts of additional measurement error due to the humidity. The LTC6804 has virtually no additional error. If the ICs are baked in a dry environment, you can see the accuracy recover. And finally, there is long-term drift. All references change over time. The changes diminish after several thousand hours. ICs using zener references have 5 times less long-term drift than ICs using bandgap references. The third cost-saving invention inside the LTC6804 is an isolated data interface. Large battery packs are modular. The transfer of data between the battery modules and the control circuit requires a wiring harness. The wiring harness will be subjected to harsh electromagnetic interference. Today, most modular battery packs use a combination of CAN communications and digital isolators. CAN offers a robust communication over 2 wires. The cost per module is around $4.50. The LTC6804 eliminates the cost and software complexity of CAN while providing robust, isolated 2-wire data transfer between modules. The interconnection of the battery modules uses the ISO-SPI port of the LTC6804, combined with a simple pulse transformer. Another IC, the LTC6820, interfaces any microprocessor to the ISO-SPI bus. The microprocessor sees the LTC6804 measurement IC as a simple SPI peripheral. The transparent ISO-SPI bus provides galvanic isolation and EMI immunity. The signal strength of the ISO-SPI bus is adjustable, allowing ISO-SPI to operate over 100 meters of cable and reject high levels of RF interference. Here we see the results of bulk current injection testing. BCI measures a system's immunity to electromagnetic interference. RF energy is injected through a probe clamped to a cable. Another probe measures the resulting RF current in the cable. Data packets are sent through the cable and checked for data corruption. The test was repeated at several ISO-SPI signal strengths. With the ISO-SPI strength set to 20 milliamps, the harness is immune to 200 milliamps of RF injection. Improved measurement accuracy, long-term stability, and ISO-SPI are just 3 features of the LTC6804. For more information on how the LTC6804 can improve the performance of large lithium-ion battery packs, visit our website at www.linear.com. Thank you.